This is Peter. We are both from Avast, Czech Republic. But what we'll be presenting today is a result of many of our colleagues, so kudos to them as well. And what we'll be talking about is a result of our research, which we made during the last 7 years. The result was on a topic of retargetable decompilation of machine code. And the result was implemented actually as something which we call RetDec. I know it is hard to pronounce. This is simply an abbreviation of an retargetable decompiler. And as a spoiler alert of this presentation, but you can read it in the title, we are going to open source it shortly after this presentation or after the conference. So, briefly about me, I'm actually a founder of this project, and in the spare time I'm working as a Threat Labs team lead at Avast, previously at AVG. To be honest, I'm messing with malware every single day. I'm making dissections of new samples, so I need a proper toolchain. So that's why we are interested in this topic. Peter, on the other hand, is a main developer of this toolchain lately, but he's with us for the last 6 years. And he's a senior developer at Avast. So much about his hobbies and activities. I know you are all waiting for your lunch, but before that, please bear with me for a few more minutes. We will make a short exercise. I guess many of you recognize that this is x86 assembly code, but please raise your hand who have to mess with such code on a regular basis. Yeah, I see a lot of hands. Thanks. Quiz time. Can you recognize this instruction set? Shout at me. ARM, perfect. Miloš, for example, over there loves ARM instruction set. So who's messing with ARM on a regular basis? Yeah, significantly less hands. 2 more to go. Can you recognize this one? MAPES, perfect. Again. So like 10, maybe 20 hands. And the last one? Anyone? Oh, PowerPC, I heard that. Good, kudos. So, how many of you? 1 hand? I didn't raise my hand because I'm not good at this one, actually. No one is perfect. So the idea why we made this exercise is that we think that it is much easier to mess with unknown binaries on some high-level form. For example, on a C language level form. You may hate C, but I bet you can read it. So it is easier to read the statements instead of some messy assembly instructions. What I'm talking about is basically decompilation. Decompilation is a reverse process to compilation. So our inputs are machine code instructions, some binaries, and we are trying to reproduce a source code. The source code will never be the same as the original one because we are dealing with a big mess inside of those binaries, but it will be close enough if the decompiler is good. Why we are doing so? There are different motives why to use decompilation. One of them, as I said, is for malware analysis. It is easier to dissect malware on this form than on the assembly code. But you can use it for vulnerability detection, for other forms of reverse engineering. You can even use it for binary translation, if you will. Luckily, there are some existing tools like Hexrace, a really great tool. I think it is an industry standard these days, but there are others. Hopper, Snowman, Binary Ninja is preparing something, and other of them. The code quality is actually quite worrying because we are dealing with many problems that we need to solve. So this problem is actually damned hard. It may sound silly, but our biggest enemy is a compiler, because compiler is removing all the valuable information that we need during our reconstruction of code. It is also optimizing the code. It is good. We are instructing compilers to do so, but whenever you need to reconstruct the code, it is a huge problem. And also there are some theoretical issues that you need to solve. For example, you are not always 100% sure whether some particular byte is code or whether it is data. So all of those needs to be solved. And of course, we are at BotConf, so we know about bad guys. Those guys are trying to obfuscate their code, put some self-modifying code in it, use encryptors, packers, and all of these needs to be solved. Furthermore, if you want to make your tool truly generic, you need to support more architectures, not just x86, but also the other ones, as I shown you previously. So you need to understand all the specifics of those architectures and instruction sets. Furthermore, different call conventions, different file formats, and so on, and so on, and so on, and so on. There are too many problems that you need to solve in order to prepare a generic decompiler. This is something we tried to achieve 7 years ago. Our motivation was to prepare a truly generic decompiler of machine code. We are not focused on bytecode, just machine code, because bytecode is a piece of cake. So we started under the flag of AVG together with Brno University of Technology 7 years ago, and we continue still under the flag of Avast these days. The project was always supported by, let's say, 3 to 4 core developers and many students. And I would like to depict that this is not a toy project, not a result of some weekend hackathon. We actually have more than 500,000 lines of code, so it's quite complex. Currently, we support 4 major architectures. Frankly, all of them are 32-bit. We plan to support 64-bit probably next year. We also support all the major file formats, as well as testing on major compilers. And because of the code complexity is quite huge, we decided to make it modular. So you are free to use any part of this toolchain in your projects, for example, detection of compilers, elimination of statically linked code by using Yara rules, whatever you want. And we support Windows and Linux. We don't care that much about Apple, but I think it is doable to support this architecture as well. Which brings me to the best slide of my part. We are going to open source this toolchain, hopefully next week. We decided to use MIT license because we think it is the least restricting license for any of your needs. We split it, the toolchain into, it sounds like a huge number of 25 repositories, but you can decide what actually you need and use it. And we will be really grateful for your feedback, even the bug reports, and even better if you will be able to fix it on your own, so to contribute to our code base. Now I pass it over to Peter, who will tell you the internals of RetDec.
So hi, I'm Peter, and I'm going to tell you in some detail how we get from binaries to C using cool technologies that we put together. Namely, the most important ones, we use LLVM as our base technology, and also like all of these, but maybe like Capstone is pretty important for us. So to do that, we need to go a little bit deeper and to look how the decompiler actually looks on the inside. we can like split it into 3 logical parts. The first one is preprocessing, that takes the binary and produces what we call image. I will tell you in a few moments what is that. Then the core part, that is actually when we use the LLVM. This eats the image and produces an LLVM intermediate representation. And the last part that lifts the LLVM IR into the source code. So let's dive in, the preprocessing part. We've got binary in the output, but in fact, it is not like one single type of binary. It is like we support 6 different formats, and we don't want the other parts of the decompiler to deal with this. So we program the file format library that is doing some uniform representation of this. This is not an actual file on the disk. It is just, there is an API in this library that lets you see the internal structures. And again, like I said, it is like uniform, so you don't need to care if it is ELF or PE or whatever. To do this, we use some third-party libraries, PELIP. It's not longer developed, so we kind of took on and strengthened it a little bit, fixed some bugs. LFIO, the same thing or similar. Then we use LLVM for Macho and COF, and then we've got some our own modules to parse the other stuff. Then we have a tool that can like dump all the information, interesting information about the binary, and also it can use ERA signatures to identify packers or compilers and stuff like that. So this tool will take the binary representation and dump JSON with metadata. We don't actually use this representation in the compilation because some malware can rely on the fact that when the binary is being loaded, the loader does some stuff and it looks different in the memory than it looks in the binary file. So we've got another library called image loader library, and this will like statically try to simulate the loading and again provide you with an API to see how it would look in the memory. And again, it can handle all the formats uniformly. Of course, there is unpacker somewhere there that unpacks like the basic unpackers and let us analyze it. Part of the preprocessing is also dealing with debugging information. Similar to file format library, there is a library that lets you uniformly represent either dwarf or PDB. We use libdwarf for dwarf parsing, that's the third-party library, and this is our own PDB parser library. So to summarize, like Jakub said, when we were developing this, it was like one huge repository, but then we spent some time before open sourcing it to like split it into small repositories that can be used on their own. So for example, you may not be interested in the compilation itself, but you may be interested in like having some library that lets you read any type of object file format. So that would be this one. PELIP, we strengthened it and added some new models, like glitch headers and delay imports and stuff like that. Similar with LFIO. PDB parser, I wouldn't recommend using this. It's not that good and we would like to get rid of it, but for now we are using it. ERA CPP is kind of an easy, simple wrapper, C++ wrapper around the ERA. Okay, the core part is when the magic happens. This takes an image using LLVM infrastructure, leaves the image, decodes the image, and produces LLVM intermediate representation. So there are some more inputs, like the metadata we saw, the debug information, if it is present, it may not be, and some databases like specification of ABIs or function signatures. So it is like a pipeline. It starts with initialization of passes, LLVM passes. So what is LLVM and what are LLVM passes? I hope that most of you are familiar with Clang. So LLVM is actually the project behind the Clang, or it is doing the heavy lifting in that compiler. If you are not familiar with Clang, it is a compiler of C, C++. How does it work? You've got C, C++ in the input. The Clang is kind of a front end. It does some stuff, but at some point it generates an intermediate representation, and then LLVM comes in and there is a lot of passes, and each pass takes the LLVM intermediate representation, does some specific job, modifies the IR, and outputs it to the next pass. And at the end, backend generates the code. So in our case, we are going kind of backwards, but the principle is the same. There are dozens of passes. Just to give you an idea, if you write a hello C, compile it with O3 level optimization, and force Clang to dump all the passes that were used, there is a chain of like over 200 passes. This doesn't mean that they are unique. There might be one single pass like 10 times repeated. To give you some idea about intermediate representation, it is kind of an assembly language, kind of a three-address code. This, like, what this does is it declares a global variable, it declares some function, it can have arguments and return type. And the value of global variable is loaded and is added to the value of argument, and then the value that is created by this add operation is stored to the global variable and returned. So if we summarize it, it is using static single assignment. That means that if we define some variable like this y, it cannot be redefined later. This holds for all the local variables. The variables that are allocated, like this global, behave like a load store architecture. It is richer than assembly language. There are functions, there are types, there are arguments, returns, but it is not as rich as C. So it, for example, doesn't have fors and whiles. The only control flow structures there are is like conditional or unconditional branches and switches. It is really, really good for any type of analysis of writing more complex passes. They are, for example, used in the compilers, but also in the compiler. So we analyze this, initialize this. So there are some passes waiting for us, but we actually don't have the LLVM IR at the moment. That's when recursive traversal decoder comes in. This is pretty much a disassembler that doesn't produce assembly, but produces LLVM intermediate representation. There are basically two types of assemblers. The not so good ones that just start somewhere and linearly decode everything to the end. And the better ones that start somewhere, usually entry point, and then follows the control flow and decodes only the instruction that it encounters. So this is the better one, the good one. How does it work? We've got our own library and the capstone library. We provide at the start, an empty LLVM module and position in it and data that are associated with this in the binary, and tell it, please decode its data, and on this position, write what you decode in the LLVM IR. It takes it and forwards the data to the capstone. Capstone returns an instruction, and then there is a lookup, and it says, if this is this capstone instruction, there is this template. Use this template to generate a sequence of LLVM IR. And the modified IR is returned, and the logic here decides what is going to be the next instruction to be decoded. When everything is done, we've got an LLVM IR that we can further analyze. This was actually the part that, like a year ago, we used something different for this, and it couldn't be open source with the old implementation, so we needed to replace it. I analyzed maybe 20 projects because I didn't want to write it from scratch, but I really didn't like any of them, so I just tried let's try what would it take to code this by hand, which sounds hard. It wasn't so bad. So for example, I was able to basic instructions for x86, 32 and 62-bit do in 2 or 3 weeks. At the moment, we've got these 4 architectures. These 3 are 32 and both 46, 64, sorry, and ARM is only 32-bit. This means that this part is already ready for the compilation of 64-bit architecture or binaries. The rest of the compiler needs some work. What else is there in Capstone? 46-bit ARM and just a bunch of other architectures. This is the place, if you want to support new architecture to decompile it, this is the place that you need to write the translation. The rest of the decompiler should be pretty much okay. So several times I mentioned the core instruction set. So how many instructions did I actually wrote semantic for? Well, not that many in the absolute numbers. If you Capstone has maybe 1,500 x86 instructions. I don't know number of how many we currently have, but not that many, 100, 200, whatever. Do we actually need more for the compilation? If you had this instruction, would you rather see this in C as the compilation result or something like this? I would argue that this is much better. This is actually how Hexrace does it. We can do this without actually modeling the semantics. Capstone tells us what are the arguments and if it is returning something, and we can auto-generate this. And this is not that complicated instruction. I picked one that actually fits the slide. There are much, much worse beasts. So I would argue that we don't really need full semantics for decoding. We only need to, for the compilation, we only need to decode those instructions that can be reasonably represented in C. Of course, when I was writing this, I was kind of hoping that maybe someone else would use it. Those guys, if you wanted to write some automated analysis on some SSA set, then you would need it. It wouldn't be easy, but it isn't that hard to write it. If you lay your ground rules correctly, you can go pretty fast. So this is pretty interesting, this for me. And if you are interested also, then I can go much deeper. But just contact me and we can talk about this later, about stuff like how it is actually implemented, how we are testing it, or how we are keeping the mapping between LLVM IR and assembly. Okay, now there is a series of level passes. These are passes that we wrote. LLVM lets you write your own passes, and low passes are those that actually use the mapping between LLVM IR and assembly. So you can ask every LLVM IR instruction to which assembly do you correspond. These are typical passes you would guess the compiler needs to make, identify variables or function or data types, and maybe statically linked code and stuff like that. At some point, we generate the assembly, and then we just dump or remove the mapping. From now on, we don't need it anymore, and we are running high-level passes. These are mostly LLVM passes, not all of them, because some of them works against us because it is compilation, but some of them are beneficial to us, and also some custom passes. So in the end, we've got LLVM IR that is lifted as much as you can, or as we can. To recapitulate the repositories, this is the main one. You can also separately use this one, but there is only the mapping here. This doesn't do the recursive decoding. So if you want to use this, you are pretty much in the same situation as Capstone. So it tells you what this is, but you need something to guide it to produce a high-quality assembly. Capstone dumper, if you are working with Capstone, this might be useful. I wrote it, and I find it quite useful. Function patterns, if you are using IDA, this is pretty much flirt implementation of statically linked code detection in using Yara. It is heavily using Yara mod, which is our library that lets you parse Yara into an IST, and then there is an API to create or modify rules. C-types, that's the database that tells you how functions look like, meaning what's their data type signature. And demangler, yeah, that's classic. Okay, backend takes an AR and produces C. In fact, we can produce control flow graphs or call graphs also. If you look inside it, there is a conversion. Backend doesn't use LLVM IR. It uses BIR, which is backend intermediate representation. There are some more optimizations and output generation. The BIR is actually pretty much an AST. So if you are familiar, if you ever had some compiler class, then you know what an AST is. If you don't, then in this structure like this. When we are doing this, we are also restructuring the code. So we can identify some patterns in the control flow and say this is not a sequence of branches, but it may look like a while or for. So for example, if we see something like this, we can transform it to if. Something like this would be if, then else. This would be some kind of cycle. This would be break. This would be continue and switch. So we are further like lifting up the representation. Optimizations, we are trying to reduce the number of variables, simplify arithmetic expressions, simplified conditions. Some pointer arithmetic is possible, and we can further like convert the loops. So, for example, this is like typical pattern that gets created, but it can be translated by moving this condition to some modified condition here. So it isn't like infinite loop that is broken by some condition, but it is like a more reasonable loop. Yeah, more optimizations. Code generations. We are trying to generate like nice code as nice as possible. So like intelligent naming of variables and stuff like that. For example, this is, I think, kind of interesting. This would be a perfectly good result of the compilation, but it is not the kind of code that you would write as a person. So can we help it? If we like map these symbolic constants to these constants, literal, and then we say, like in the context, we cannot do it everywhere, but in the context of a socket function call, we can do something like this, which is definitely much better. It can be even more complicated. So for example, number 7 can be created by logic AND of these 3 symbolic constants. Finally, we generate the output. Backend is pretty much only in the RetDec, the main RetDec repository. So how was it possible to use this? So up till now, it was through the compilation service. It was on the web or our API. From now on, after we open source it and push it to GitHub, you will be able to build it yourself. We are using CMake, GCC or Clang on Linux, and Visual Studio, only Visual Studio on Windows. And then you need some prerequisites and the typical CMake build. You run it simply by running some bash script that ties it all together on the binary. Or you get the IDA plugin. So what's the IDA plugin? The stuff that Jakub was showing. This on the right side is not actually a hex race. This is the output of RetDec that is like embedded into IDA. The goals are it should look native and feel native. It should be interactive, and it should use the same names and objects and everything that IDA uses. How is it done? You let IDA to analyze it, analyze the binary. You can change stuff, as you will see in the moment, meaning like rename something or change whatever you want. And then when you activate the plugin, it will dump everything to, again, JSON metadata. And this will be used to feed the build of the RetDec, and it will try to use everything. So the names that it will output, the names of the function and stuff like that will be the same as in IDA. It generates the C, and then you ask IDA, please show it. This can be replaced. If you don't want a local build, you can use the API and decompile on our servers. So it is interactive in the sense that this cool highlighting is done by default by IDA, but I could go here, for example. No, not here. If there was a function called here, I could double-click it, and it would automatically decompile it and show it to me. I could then jump forward and backward. There is a context menu, so menu that is shown for functions is different than menu that is shown for global variables and stuff like that. It isn't as good as hexarrays because we are kind of simulating all of this somehow. We cannot be just as close to IDA as hexarrays is. Okay, so how was it used so far? We got this web page for, what is it, 3 years nearly. There are like 12,000 registered users and around like 400-something thousand compilations. I don't know if it is good or bad, but I know that decompiling through web interface isn't like that useful, so whatever. I think it will be much better when you can download it and build it yourself. So this is what I talked about. Example of IDA plugin on sample that's called WowTrack. That's some kind of malware. This one had no symbols, had anything, had nothing. So someone, I think it was Jakub, actually analyzed it and set, for example, the name of this function, set the names of and types of arguments, set even the positions or the objects that the arguments are passed in. If you did it in hexrace, of course, it would use all the information. We do the same. So this is our decompilation of the same thing, and everything is the same as in IDA. This is another example. This one, our code is actually like a little bit smaller and more compact, but in general, I must say that hexrace code is better and usually more compact and easier to read. This might be a pain in the ass. If you have something like this in IDA, it is a switch table. IDA can recognize that it is a switch table, but actually finding out what it does is not so easy. So hexrace is able to help you, and we are also able to help you just the same on this particular example, just reconstructing the switch. This is the Cybot malware. It was attacking MIPS, I think routers, I'm not sure, but definitely for MIPS. So IDA could, or hexrace couldn't decompile this. This one was actually packed, but after you unpack it, there are symbols. So this name is like a real name from symbol table. If you like deep or dive into the code that was decompiled, it actually makes sense. So this function does the same thing that it is named for. And this is the example on the Cybot of the call graph from main function. Okay, so now after all this, do you even need hexrace or should you throw it away? No, I wouldn't. IDA and hexrace are great, and the output quality is definitely better than us at the moment, especially when the last year we were kind of focusing on open sourcing and rewriting those parts that couldn't be open source and not so much in quality. So I think it would be possible or easy to increase the quality rapidly now when we got all the groundworks, but at the moment, definitely better than we are. It is interactive, it is seamlessly integrated, it is much more mature, and there are many plugins, and of course, it is their business, so they will support you. It is not perfect, however. It's not free, it's proprietary, and it is kind of a big GUI application. So if any one of you would like to hack it or just use some part of it, it wouldn't be so easy. So obvious reasons why you might want to use RetDec. It is free. There is a MIPS architecture that isn't in hexrace. Hopefully there will be more because like I show you, the capstone can do much more. Good license, and you can play with the sources. Not so obvious reasons. LLVM is really awesome. If you want to do any kind of more advanced, maybe something analysis, maybe something from academia or something like that, it is much better to do it on this than on any kind of assembly. You also maybe notice that the basic principle is kind of different. We work more like a pipeline. It is a command line tool. You can feed it whatever and it will just go through it. Hexrace is definitely better when you are kind of an analyst that wants to interact with it. We can simulate it, but not as well, definitely. So I'm not sure if I mentioned this, but LLVM is really great, especially with combining of this. If you are willing to hack it, you could take this and make your own tool just custom for you. It wouldn't even have to end up in the compilation of C. It could just, you would just pick your own passes, maybe write your own passes, and just stop it somewhere, and you would be happy with your result. For example, you would just dump some information into JSON and consume it by something else. Okay. Also, RetDec is not just one tool and one repository. Like I said, you can use any of these pretty much as you want without the actual decompilation. So what's next? We will open source it, I think, next week. And then we will have a release party in the office. And then probably some sick days. Then if you try it and it won't work, please write us. We will be very happy if any one of you tries it, and we wouldn't like to end it like, yeah, it didn't work, whatever, screw it. So we will be happy to help you. Then I think there might be a group of people that would be interested in more details of what we actually do, because it might seem like I said a lot, but to really dive into it, it would be like a full university course. Yeah, and maybe we'll try to make some more presentations, probably on LLVM Dev meeting. And then, of course, improve it. Make it a little friendlier to Windows. Get, of course, support 64-bit architectures. And there are definitely some libraries and modules that I would like to get rid of and just replace them with something better, like the PDB parser. And then we will see. So thank you. And if you have anything, write us to this context. Thank you very much.
Thanks a lot for the presentation. Are there any questions? Oh, there is one here. Who has the mic for the speakers? Yeah, there is one here. Yeah.
So first of all, amazing job, guys. I wanted to ask, I saw that you deal with a lot of...
We are actually supporting something which we call raw code decompilation, so it can eat raw bytes. So yes, we support.
Great, thank you.
Any other question? No? So thank you, gentlemen.